Okay, welcome everybody to our next webinar from the IEAGHG Greenhouse Gas R&D Programme, or IEAGHG as we're known. The topic of today's webinar is CO2 storage efficiency in deep saline formations. This is work that we've been undertaking to improve the ability to determine the capacity of CO2 storage and moving on from the volumetric and static analysis to dynamic. Just a quick introduction to IEAGHG. We're part of the IEA's Technology Collaboration Programme. We have 33 members from 18 countries, OECD and non-OECD, plus OPEC, the European Commission and CIAB. Our members set our technical programme direction, and we are a technically based organisation, an R&D organisation. We don't prescribe policy and we don't advocate for any one particular technology. Our focus is on technology options to reduce greenhouse gases from the use of fossil fuels, and our main technology of interest is carbon dioxide capture and geological storage. We do many things in this technology area, capture, transport and storage, including running our networks, research networks, the studies that we do, which this webinar is based upon, and our main conference as well. And our objective is to provide our members and our policy audience with independent technical input. And thank you very much to our members here, who you can see, who fund our programme and enable us to do this. And we make sure that our work also goes into various bodies so that it's used where appropriate, such as in the UNFCCC, in IMO, ISO, CSLF and ZEP. So our presenter today is Dr. James Craig. James is our senior storage expert, technology analyst here at IEAGHG. He's been with us for 4 years now, and he looks after the storage area. He looks after the risk network and the modelling network and many other things, and has a good background both in CO2 storage and renewable energy technologies as well, and started originally with a PhD in geology and geochemistry. So with that, over to you, James. Thank you.
Well, thanks for that introduction, Tim, and good afternoon, everyone. So today I'm going to present a summary of two research projects which we contracted from the Energy Environmental Research Center, which is part of the University of North Dakota and is one of several centers of excellence in the United States which do work in the subsurface in different capacities. And this work was funded through our program, but also co-funded with US Department of Energy, and I'd just like to acknowledge their support. So today I'm just going to run through the objectives and then talk a little bit about the model development and how these models are constructed, and then talk about the results from the modeling. And this was a two-stage. These were two separate projects, but in fact, effectively they are linked and trying to address the same question, and then bring the whole topic to a conclusion. You will notice the map in the bottom right, which just highlights the distribution of deep saline formations, which are prime targets if we are serious about large-scale CO2 injection. The orange areas being those prospective formations, which, as you can see, are distributed fairly broadly, both on and offshore. So, when this project was set up, the real question was comparing volumetric and dynamic storage methodologies, really to try and improve estimate of what could realistically be stored at large scale in deep saline formations. In the first stage, two quite distinct formations were selected: the Minnelusa Formation from the Powder River Basin of Montana and Wyoming, and the Qingshankou-Yaojia Formations from China. And apologies to those of you who might have a better pronunciation in Mandarin, but they were quite deliberately chosen because they have separate sedimentary characteristics, but also in terms of the restriction in terms of fluid migration, which I'll come on to in a minute. So in the Minnelusa, we have it's predominantly aeolian dune sedimentary formations interspersed with carbonates, whereas the Chinese formation is largely composed of deltaic fluvial deposits separated by Castrian muds. You should also note the scale of the formations, which are within different basins. It's important. Most of you will be familiar with this concept, but I do think it's important to just be clear about what we mean by open and closed systems, because they are fundamental to storage capacity. With an open system, we're talking about permeable formations which can have hydraulic communication, possibly with the same formation but over large areas, whereas with closed systems there may be faults, strategic pinch outs, or even structural features which effectively form impermeable barriers, creating a closed system. Okay, so this whole modeling had to begin with a geocellular model. That is a model of each formation based on its geological properties. So what IEAGHG did was to construct a volumetric model of each target formation from structural contour maps, isopack maps, facies maps, geophysical well logs, core analysis, and general geological interpretations, which collectively they used to produce a 3D geological model with a contoured surface top and base, so they could then get a thickness and then project this formation across the entire basin. Different, if you like, storage properties in terms of zones are created by interpolating between grid points from the information that I've just mentioned, including isopack maps, and that was keyed into well log tops. A porosity permeability filter was applied, so basically trying to form the optimum volumetric capacity of each basin. Hang on, I've gone on a bit too fast. So, can you get back on, Sean? So, so the total pore volume of each formation was refined from that compiled geological information, and as I've just previously mentioned, porosity, a minimum porosity permeability was then applied, and then the pore volume was calculated based on P10, P50, and P90 conditions. So, model development looked at a number of simulation cases. We don't have time today to go through all of them, but I've selected those which are give good examples of conditions which affect the storage capacity. The storage efficiency values were developed taking into account physical, hydrodynamic, solubility, and residual gas trapping. And several cases were run over different time periods. Okay, so just to be clear what we mean by storage efficiency, this is defined as the estimated storage capacity determined by dynamic modeling, expressed as a percentage of the theoretical storage resource, which is represented by the total pore space. Now, before dynamic modeling was considered, obviously there had to be a starting point, and when deep saline formations were targeted, the pore volume of target formations had to be estimated, but that only gives you a volumetric estimate. The dynamic effect of pressure and time is really what's critical, and these projects were designed to do just that. And what you will notice in the graph, and this is the Minnelusa Formation, is the difference between the two volumetric estimates, that is a high and low estimate, and the high, medium, and low case for dynamic estimates. And you'll notice there is a big difference between the two, which is an effect of the dynamic influence. And in this graph, you can see basically it is quite deliberately extended over 2,000 years, which is just to give a theoretical maximum and to see the effects of time. But in actual fact, the simulation has been extrapolated from the first 50 years of data. And that shows with continuous injection, only 7 to 12% of the storage occurs in those first 50 years. And the remainder takes up to 500 years before 50% can be stored. So it does show that injection into this sort of formation to achieve the sort of levels equivalent to a volumetric estimate take a very long time. And here you see the same effect, but here in a bit more detail. And it shows quite a big spread between the storage efficiency, assuming a medium case P50, a low case P10, and a optimistic case P90, which shows what it reflects is the degree of uncertainty and heterogeneity within the formation. Turning now to the Qingshankou formations, the Chinese formations, the difference between the equivalent P90 to P10 is very small here, and that reflects the fact that this is a quite different formation with much poorer storage properties. What does make a difference here, and what the graph shows here, is the level of increase that can be achieved with extraction. So these results, these dynamic modeling results, show the variation that can be achieved assuming different wells. Now, I should stress that these wells are uniformly spread over the entire basin area. So again, it is a theoretical maximum. It also shows the degree of solubility trapping that is achieved through time, and that can vary depending on the scenario. But if storage could be achieved over 2,000 years, it could be as much as 50% in both formations. And here we have a very clear example of the contrast between modeled estimates for both these contrasting formations. You will notice that within the Minnelusa there is a big difference, as I've said before, between the P10 and P90, whereas the Chinese system is much closer together, and this again shows the contrast in the geological environments and the storage properties. The Minnelusa being an example of a more open system compared with the closed system of the Chinese formations. The modeling, we're still in stage one, and the modeling attempted to show the variation in storage efficiency that could be achieved with varying degrees of wells and orientation. And as you can see, there is increasing the number of wells up to as much as 820 does not necessarily improve the storage efficiency to any marked extent. And this is a phenomenon we'll see later on. Again, this is the same pattern, except the difference between the different wells in the Chinese formations is even less. There is even a less distinct difference between the smallest number of wells and the largest number. And again, what this reflects is the type of geological formation and the storage efficiency. So let's now move to stage two. One of the rationale for moving to stage two was partly because it was recognized that trying to extrapolate over 2,000 years was not really very representative of the likely scenario that industrial scale storage would incur, and also to get a better handle by looking in detail at storage over a shorter time scale. So the modeling was done over 50 years. Again, two deep saline formations were selected. One of them was the Minnelusa, which I previously discussed, and that was partly because we already had good information on it. The other was the Bunter Formation, which is widespread across the southern North Sea and is a prospective candidate for CO2 storage from the UK and continental Europe. Again, several different scenarios were tested to see what effect they had on storage efficiency. And again, the modeling was designed to contrast the effect of closed conditions, open conditions, brine extraction, and indeed salinity. So the selected model areas were much smaller. You can see on the left in the Minnelusa, a much smaller area was selected rather than the whole formation, and approximately the same size area was also selected from the Bunters to give approximate comparability in terms of area. The Bunter model was actually taken by a model produced by the BGS for a North Sea appraisal of prospective storage sites. So, as you might expect, and now bearing in mind we are talking about injection over a 50-year period here now, the blue line represents the storage efficiency produced by the model as compared with the volumetric efficiency, which is the orange line at the top. And you can see that in 50 years, in this case, in the Minnelusa, volumetric efficiency is not nearly met, which is what you'd expect. The other point to take away from this, that once you get past 90 wells, the storage efficiency begins to fall off quite substantially. So in other words, if you like, the storage efficiency doesn't increase just because you add increasing number of wells. And of course, in future, this will be an important consideration, because there will be an efficiency point where the number of wells required will need to be decided. And the next slide shows the same effect here for the Bunter Formation, but the volumetric efficiency is much higher. It's at 14% and quite outside the graph scale. So it's not included here, but a big contrast between volumetric and dynamic efficiency. Again, you see this fall off in the number of wells. Once you get to about 90 wells, efficiency falls off quite substantially. Although this is modeled, this is extrapolated to 100 years, you will notice, this is the Minnelusa, this is modeling results. You'll notice there are two striking points here. The middle three lines here are effectively optimistic base case and most pessimistic case for an open system. Contrast that with the lowest line that you see there, which I think is purple, make out is purple. That assumes a closed boundary, and you'll notice there is a big contrast between in this case, the amount of CO2 that can be stored in the system. And then, if you like, taking the other extreme, if you include extraction, certainly after 50 years, capacity increases quite substantially. Sorry, that's Minnelusa. So the next slide. Oh, sorry, go back. The next slide shows the same phenomenon, except, of course, the different cases are much closer together in the Bunter Formation. But again, what is very striking is that in if you assume closed conditions, capacity is much reduced. And we see this summarized in this table, which shows just how substantially different closed conditions are as compared with what is assumed to be an open condition, and in two other different structural configurations. Notice that with the same number of wells are applied, but there is also, in terms of percentage efficiency difference, it has a big effect on capacity. Now, what was also done in the Bunter was, and I'm just showing that the report does include a number of other different scenarios, but I've deliberately just selected a few just to highlight contrasts which the modeling results have produced. And in this case, a comparison was made between concentrated well formations, which you might expect from an offshore platform, as compared with dispersed wells. They're perhaps not too easy to see, but on the left-hand side, the concentrated wells coincide with the dome peak in the center of that image, whereas the dispersed wells around the fringe of that structure. And you can see the results here represented in a tabulated format, which show, as you might expect, higher efficiencies and greater capacity if the wells are dispersed. Of course, there could be cost and economic implications of that, because this is an offshore site where the likelihood is wells will be drilled from platforms, and although deviated, the distribution is restricted a little bit by technology. And okay, so in terms of solubility, which was another feature to examine, one of the questions raised from the stage one was the effect of solubility on, and indeed trying to model solubility. And what you notice from this table, that if you use a model with a larger grid cell size, you will, not surprisingly, perhaps, given that salinity and temperature are constant, that the assumptions you make in the model affect the efficiency. If I move to the next slide. Okay, so what you see here is, again, the effect of the cell size used in the model. But in this case, we wanted to model the solubility, and what you find is that with a larger cell size, the effect of the model is to give a higher level of CO2 solubility as compared with the smaller cell size. So again, trying to estimate capacity, which does vary, as you can see from the column of the dissolved CO2, depending on the assumptions you make and with the model, will affect the capacity estimate. Now, of course, with a greater number of cells, there is higher demand on computational resource. So there's always going to be a compromise with the assumptions that are made. With the Bunter, the effect of well distribution and the quantity of wells, as was previously shown, does have an effect on capacity. And what this model output shows is the saturation, of CO2 within the reservoir. And what you'll notice, of course, is that the highest levels of saturation around the periphery of the model area as compared with CO2 in the center. And the interpretation of this is that it is a pressure proximity effect, and that assuming in this case it must be an open system, that if you like, the internal injection area, there is a pressure interference, which explains why there is less CO2 dissipated in the center of the model area as compared with the periphery. If we now look at what happens, the same phenomenon, but now include extraction, you'll notice that the storage efficiency where there is no extraction, which is the top image, compared with the lower image where extraction is assumed, storage efficiency goes up, and that is what you would expect. But of course, what you're trying to do with all this modeling attempt is to at least get a first approximation of the level of efficiency and capacity that can be achieved with extraction. So I included this. It's not really meant to be something to show an exact comparison. It's merely to show what effects, what assumptions can have, and the effects of modeling when you try to compare a large area in stage 1. This is for the same formation, by the way, as compared with stage 2, which is over a much smaller area. And you'll notice that with a much I wouldn't say bigger grid, but a grid with smaller cell sizes, and therefore one you would expect to be more accurate, but obviously over a smaller area, gives you much higher storage factors. Of course, the well density is different as well. The interesting point also to note here is that the closed case is very similar in both circumstances. Before I move to summary, I would welcome any questions that you may have. We do have some time at the end, but I would now like to move to the summary. I think we can, certainly what the stage 1 demonstrates is if dynamic injection is assumed over a long period, storage efficiency starts low, rises quickly, and then levels off in an asymptotic trend in much the same way as happens in oil and gas fields. Optimization can increase storage efficiency and increases the maximum storage efficiency. Dynamic results become roughly equivalent to volumetric efficiency values after about 500 years. So what that implies is that what is commonly done with volumetric type of work is to include a storage efficiency factor. So whatever factor is used has to be broadly representative of what might happen in a volumetric system. The biggest single factor, as might be expected, is the extraction of saline. There's a much bigger difference between the P10 and P90 in an open system as compared with a closed system, which reflects the geological and reservoir suitability of formations such as the Minnelusa. And between 15 and 33% of injected CO2 could end up in solution after the first 50 years, but this percentage could be further increased slightly, between 16 and 41 over 2,000 years. Now moving to stage 2, which you'll recall is over a much smaller area and over a much shorter time period. Brine extraction again has a very significant impact on storage, almost not quite doubling the storage efficiency. The biggest influence, though, is the effect on whether you assume an open or a closed model boundary. The injection rate and cumulative injection can vary considerably with grid size, assuming salinity and temperature levels are constant. Larger grid cells result in lower injection rates. The incremental efficiency factor is very small when more than 90 wells are exceeded. The percentage of dissolved CO2, assuming uniform salinity and temperature conditions over 50 years, can depend on the grid cell size used in the model. Larger grid cells produce higher estimates of dissolved CO2. The model showed that well configuration can influence storage efficiency, and there is a notable decline if the well's concentrated. Now, I suspect in reality, if you had a platform system, as in oil fields, the optimum locations would be targeted to get, if you like, the least pressure interference, but the most capacity and injection rate. But obviously that's well outside the scope of this particular study, but just a thought for consideration. And again, open and closed boundaries are very important when trying to define the capacity of potential storage formations elsewhere. And of course, we shouldn't forget that the fracture pressure of reservoirs will be a constraining factor, and obviously needs to be included in the model, because there's always the temptation to exceed what that might be, and that's going to give an erroneous capacity figure. So where do we go from here? I think it's quite clear that efficiency factors should be supported by key values that influence them: the grid size, domain dimensions, formation boundaries, especially excuse me, whether there's hydraulic communication. Because some of these formations do are quite extensive, and the level of hydraulic communication between them and other operations is a significant factor. And as I said previously, the efficiency factor should be based on, or should include, whether it's based on an estimated or a measured caprock threshold. Obviously, the efficiency factors need to be expressed as a range from, including base case, conservative to optimistic. Really, the injection period is arbitrary, but 50 years seems to be a reasonable assumption for industrial scale operations. And indeed, the injection rate should also be stated. As you can see, and as I've shown, the rate does depend on distribution and number of wells. And really, I'm sort of thinking aloud as to, these are the steps really to be taken to refine further attempts at large-scale capacity, dynamic capacity estimates. And I would be happy to take any questions. You might notice there, I believe that is an onshore image of the Bunter Formation.
Okay, thank you very much, James. And I was about to ask you the relevance of that photograph there, so thank you for that. We had a question early on that related to whether some reservoirs and basins can be defined as closed or open, but I think your presentation has then moved on to describe closed and open scenarios in the modelling.
Yes.
So I think that question was answered actually as you presented. Where do you think we should go next in this work, and where are we thinking of going with our technical program?
Well, it's not just other people are thinking about this. Really, it's trying to improve the approach and methodology of dynamic modeling. As you'll appreciate, every basin, well, not every basin, every prospective formation has a degree of unique characteristics And really, to build the sort of detailed model, as I explained earlier on, ideally you need a lot of well log information, geophysical seismic profiles to build those models. If they're not available, which is commonly the case with deep saline formations, then modeling becomes that much more important. So the question then is, how much reliance can you put on these models? What modeling approaches can we develop and apply which give a reasonable estimate of the dynamic capacity?
Okay, so we have another question. Did the study consider the options for the handling of brine after extraction?
No, it didn't. In short answer, this is a question which is being raised more frequently. And interestingly enough, last week, US DOE annual conference are actually looking at brine treatment in the middle of the continent. It's not so much an issue in place offshore in the North Sea, provided there are no contaminants in the brine and that it is released in a controlled manner so that it doesn't have any deleterious environmental impact. What's happening in the US now is potentially brine treatment for onshore. And it's at a very early pilot stage, so the results are yet unknown. But I think it needs to be appreciated with the scale of resource that we have for doing this kind of work. We would really need and might well do a separate study on that.
Yeah, and I think there's projects in the US they're called the BEST projects, aren't they?
Yes.
Brine extraction.
Yes, that's correct.
Something.
Yeah.
So they're an area to watch, and I think we did do a study on brine extraction and water treatment 5 or 6 or 7 years ago,
we did.
And we are in fact considering updating that that study. So, do we have any more questions? Okay, are you, James, after this study, any more or less optimistic about future CCS potential globally? That's a good question.
It is a good question. If you look at the history of CCS over the last decade, as you might expect, and as we move to larger scale operation, we're seeing a diversity of success rates. Cases like Insala would perhaps tend one to think of this as being pessimistic, whereas Sleipner and the evidence, I think, from Decatur would suggest that if you have open systems with good permeability and good characteristics, there is quite large capacity. And in fact, I believe the Carbon-Net project offshore Victoria, the preliminary results from seismic and from petroleum exploration show that there are some very promising large-scale formations. So I'm tending towards the fact that I'm tending to be more optimistic now, but I think we've got to be realistic about how many good formations there are out there for dealing with very large capacity. And also, of course, you might find that some formations may be less suitable, might require more wells, might have less capacity, and therefore be much less economic. But I think there is certainly room for optimism.
Okay, thanks, James. And in fact, we just had a related question to that. about whether this supports or erodes public support for CCS projects. I think you've answered it in that answer just there. A question just on, is there an adequate grid size for estimating the amount of CO2 dissolved?
I don't know. I can't give a straight answer to that. I think perhaps needs a bit more work on it. I certainly think the grid size used needs to be clearly expressed in any estimate.
We can come back and answer that question.
Yeah,
Questions we run out of time for, I can just say that we will answer by email afterwards. We make a note of all the questions.
Yeah, indeed. I mean, the point I would say is that generally speaking, the smaller the number of grids or the larger the number of cells in the model, you should be able to get a more accurate result. It is always a compromise with computational resource. So I'm not clear about what might be the most suitable for this particular estimate.
Yeah, okay. So I think we're coming up towards the end of the time that we've got. So I'll ask one more question, and that's how do these capacity estimates compare with those for CO2 EOR capacity estimates?
I'll need to come back to you on that one. It is, for one thing, CO2, most CO2 EOR is commercial, but it is happening at, if you like, some sites. Particularly, I'm thinking of the work that Patel are looking at. Caution there, because their target reservoirs are pinnacle reefs, so the storage efficiency is not directly comparable with deep saline formations. It's a good question. I would certainly need to come back with a more detailed answer on that one.
Yeah, it was about the capacity estimates as opposed to efficiency estimates. So I think this doesn't change the case that we think the potential global capacity in deep saline formations is much greater.
Oh yes, I don't think there's any question.
Reservoirs,
I don't think there's much question about that. And what is very significant is the lateral extent of some of these formations. Not surprisingly, they've not been investigated with any degree of rigor because up until now, they've not been of any commercial or economic or social interest. But I think there is evidence of certainly some offshore formations around the fringes of continents like South Africa, Australia, possibly even South Korea, certainly North Sea, and even the United States, where they are very extensive.
Okay, I'm afraid we're running to the end of time. Thank you very much, James. Thank you very much for all the questions that came in. There's a couple more that come in, and we'll answer those by email afterwards. And with that, I'd like to thank you all for listening today. I hope that was interesting for you. And please follow up with emails afterwards with any further questions you might have. So thank you very much.